right, welcome back. We were in a super jovial mood this morning, so we'll do the best with that. I wanted to start to really connect a little bit more what we're doing in lab with what we've been covering, and I think you'll start to see more and more of those connections today and going into next week. Um, where we left off was talking about just shaders and what they look like, and I think as you worked on MP3, it's a little unfortunate that a lot of teams didn't really get to that point. And I understand why. From the perspective of what you were trying to implement, you were really just treating the shaders as just this test code that has to work correctly, that has to give it a result that matches visually what I expect to see when running the code natively. And I understand that from just sort of it was treated as a test input versus something that you could really start to dig into deeper and understand what was happening and play around with different things. That's something you have the luxury of doing once you have the assignment completely working, and that's been the case, I guess, all semester. That we've gotten things generally working, maybe a little bit less so for MP3 than the previous ones, but not with enough extra time to sit back and reflect on it and maybe dig a little deeper as need be. And that's that's kind of the challenge we face, I guess. We get enough done just to catch our breath and recover and move on to the next thing, and not really to do that deeper exploration that I would love to see. And in an MP3 maybe more so. So I think it's the case that for many teams, even to the extent you have your vertex shader working, you may not appreciate all that's happening, and you're saying, okay, input comes in, output looks fine, we're done. Whereas to really debug these things, you would in theory have to provide more and more, test inputs, understand what the assembly output winds up looking like, and how that all engages with the hardware that you've already built for your vertex shader. So, I mean, I can show various shader codes, and we can show them running. In general, the type of trigonometric and algebraic operations one needs to see to be able to do computer graphics is what is supported in the various shading languages, with your vectors and matrices as sort of built-in types, with the expected operators also kind of built in and supported, such that you almost never seem to have to be able to write um, I call it a sort of low level shader code that for anything that you want to do mathematically with your incoming attributes, there is generally already a built-in function to do it. So you can write your for loops and kind of reinvent things from just low level additions and subtractions and multiplications, but you almost never need to, because if there's an operation that a shading model expects you to have, in general, these things are kind of co-designed together, the algorithms and the languages to support them, so that that function generally exists. So we were talking about the long list of kind of built-in things, and we left off last Thursday with where a couple of challenges of how do you rewrite this code to not use certain operators, and we could continue to do that, but in general, we're going to see as we look at lighting models that a very common thing is to do either dot products, or sometimes also to do cross products, to normalize vectors for lighting, to reflect things for lighting purposes, and all those are just natively supported in the language itself. So I won't actually talk right now about how this is implementing a type of diffuse lighting model, but we will get to that in just a few minutes here. But in general, you can almost always directly go from straightforward mathematical description of what a model for shading is supposed to be doing, to a vertex and or fragment shader that does exactly that. And the lighting models themselves tend to have a lot of parameters to them, so the code can sometimes look lengthy just due to the total number of parameters of what you have here. But the actual math for it tends to be really straightforward, built-in functions that you're heavily leveraging for your code. Whether those built-in functions correspond directly to function units in your hardware is something that we already started to explore in MP3, and you may explore further. There's no guarantee that there's a one-to-one relationship between a normalized function in your shading language and an ISA that includes normalize as an actual instruction that can be calculated in a set number of cycles. So when we would talk about how the shading language is something of an API, is also something of an ISA. There is a lot of overlap there because the two things do tend to co-evolve with each other. If these operations are seen as critical from an API perspective, mathematically we're wanting to do normalization over and over and over again, then it stands to reason that from the hardware manufacturing perspective and designing the architecture, there's a good reason to have normalization as a built-in as instruction with its own functional unit associated with it on the chip. But there's no guarantee that's the case because for all of these operators, there's multiple ways you can do it. And we've started to see that. And then the pressure is really on the assembler or the compiler to take those operations and either convert them into sort of native assembly instructions that have their own dedicated function units, or to figure out what the sort of micro-coded or software emitted version of that same operator is going to be. And I think that's something that would be nice, that if you have a chance to explore, and it probably won't be until you get to the project stage, where we mention, well, we can do square root. We have an instruction for square root. Well, we're seeing that building that in hardware is doable, but it itself may take a few weeks, maybe even more than a month to do properly. Well, now that if we really, really want square root functionality for our shader, for whatever computation we're interested in doing, we always have that option of effectively emitting a software version of that, taking the same exact algorithm that we perhaps would have wanted to implement in hardware with measuring the performance of it in clock cycles, and instead emitting equivalent instructions for things that we do support already. So your additions and your multiplications and the like. Sometimes that's a little tricky if you're not also supporting branches, but that is a way you can always support any of these operations. It'll get encoded as the operation in the mid-level assembly and the pseudo assembly that is emitted for our SBRV. You can take that and then generate whatever really you'd like to with it, either a native instruction, um, or for other purposes. Square root has lots of purposes. When we're dealing with our standard shading model here, I don't see it all that often. You see exponent a lot or the power function quite a bit, and a lot of these kind of just vector operations for lighting. Um, in theory, anything you would generally want to use square root for calculating distances and things like that, that's what you would see it for. And we oftentimes do need to know in the shader how far away is this from something else in that Euclidean distance space, and that's where you would see your square root operator. Um, we see a lot of shaders that explicitly try to avoid using square root, not because it's not implemented, because it still has uh, performance implications of using it. Here's an example where it's actually sort of a built-in of the vertex shading spec, where you can actually specify the different point sizes. And in this case, it would be an example of a shader that's doing a forward transform, doing the basic model view projection matrix transformation, and is actually also figuring out based on how far away we are from the camera, how far we are and the eye distance, make the points if we're actually passing points through of a certain size. Um, for MP1, we were using a constant larger point size so you could see the actual GL points. But this is something that in theory we would have to support in our rasterizer as well. Right now we don't, right? We get a GL point in our rasterizer um, of the primitive type, and we just pass them through. For every vertex that represents a point, we just generate one fragment, essentially, is what we wind up doing. That was our MP1 basis, and in MP2, we continued that as well. But one could build a point renderer that, given a point size, you're actually having to generate fragments in a neighborhood around the specified point. That should be very doable in a relatively straightforward state machine. Given a point size and given an XYZ position, generate points around that place in that three-dimensional space. Um, Not necessarily enough to make a project idea unless you had something else you wanted to do on top of that. But that adding to the rasterizer to support other primitives would be perfectly valid as the starting place for one of your projects. Lots of different things you can do in the fragment shader. We talk about fragment shaders as being quote unquote more expensive than vertex shaders. Um, the hardware is the same, right? So in our case, we see as we have our MP4 hardware, literally we're sort of copy pasting the hardware. And in modern systems, it's the same physical hardware. It's not even in a different place in the pipeline. We refer to fragment shaders as being more expensive from a performance perspective in the sense that there's just more input, right? There's almost always going to be more fragments and significantly more than there are vertices for a given scene, right? So because we have a triangle that's only three vertices, but that could be potentially thousands, millions of fragments associated with it. And even for very small triangles, you're still generally having more fragments than you have vertices. So when I refer to that, or when you hear that term that your fragment shading is more expensive, that's all that it means. It's roughly the same exact ISA, if not an equivalent ISA. It's doing the same exact type of things with its computation. It's just has a lot more threads associated with it. That's one way to think about it, right? There's just that many more fragments than there are vertices. So from a performance perspective, um, it really depends on your needs, of course, but you do sometimes see a case where more of the heavy lifting, when we look at lighting and shading here, is being done at the per vertex computation versus pushing it all off to the per fragment computation, just based on that sort of fundamental asymmetry there. This example isn't doing anything. That's our sort of pass through or our just color calculation one. We could invert the color components in our fragment shader. That's something that again, because these vectorized types are sort of natively supported, you can do scalar minus a vector and get an equivalent length vector back out with just one line of code. Yes, you could do that for each component separately, but then you don't need to because of what's supported in the language. Various different ways of doing sort of grayscale conversion, or in this case, this one's also doing kind of sepia conversion here. Those weights depend on the different standard for conversion that we're working on, but that kind of computation, which my understanding in 488 is forms something of the basis of one of your assignments in that class, but that computation in our fragment shader becomes a relatively um, straightforward thing as well. Now, you could also do this in the vertex shader, as I just mentioned, that given an input color to the vertex shader, you could calculate the gray and convert it to a grayscale thing as well. The difference is really effectively how flat or how continuous the resulting model or scene is going to look like, right? Where the interpolation is actually happening, right? Is it happening based on RGB color information, which is then used as input here to calculate how gray the result should be, or do we calculate how gray each vertex is and then just interpolate that gray value across the individual fragments of our triangle, or here for the sepia calculation? It'll give a different effect, even though the math is exactly the same, right? Calculate gray based on RGB. Here it's just a simple dot product and interpolate across the triangle, or interpolate all my initial colors, RGB colors, and then calculate the gray. The math is basically the same, right? We're calculating a gray value for each fragment inside our triangle, but it's going to look a lot flatter. You're going to be able to see each triangle as having more pronounced edges to it if you're doing it at a per vertex level versus at a per fragment level. So it's not necessarily a trade-off just of performance. The actual resulting image quality is also going to change based on where you're doing the computation, and we kind of see this over and over again. Do I want to apply this shading model on a per vertex basis or a per fragment basis? Oftentimes, the mathematical basis is exactly the same in terms of input color or input attribute to output color relationship. And ultimately, all of shading is determining a color, right? Ultimately, we have these pixels on a screen and we're determining what color that pixel should be. The trade-off is how much of that computation can be done on a per object basis, per vertex basis, or ultimately on a fragment by fragment basis with quality and performance trade-offs that are being managed based on that. This one is doing fog calculation. So something that used to be have dedicated hardware specifically to calculate fog distance and to do this computation in fixed function hardware is now something that, because we support those instructions natively in our programmable shaders, is something that can just be a 3 or 4 line shader. So it does reflect a pretty significant change in how we describe what is happening in our scene. And so, we've been talking about, well, it'd be really nice if we could demo that GL Quake for any of our assignments for your final project. And I've been hesitant. I've been looking at the code. Uh, Code that's written in fixed function OpenGL, and there is no tool. And I think there's a reason there is no tool. Just does not translate that easily to code that uses programmable shaders. In theory, it is doable. In practice, I think the issue is just the quantity of work involved is probably a bit too much because things like your lighting calculation, things like your texturing, that was all used using API calls directly to specify the state of the computation in our OpenGL as one big state machine. And now there's still some state functions we use, and we've been using them all semester, and the rest of it is in these programmable shaders. And so that conversion from something that's doing fixed function lighting and fog and texturing to something that is just a collection of shaders, I still think it's doable. There's nothing conceptually that makes it impossible. I keep saying things are doable. I just think the lift involved with that is probably just a bit too much. It's too much for me, and I think it's too much probably for you in the time associated with this semester. But this is just another example of what can be done. So it's the same exact math that we used to have OpenGL calls to calculate. What is my fog distance and what is my fog density, which we could specify uh, for each color channel. And we're calculating the second order exponential factor. So it's taking that value based on how far away the object actually is in our fragment, in our pixel space here, squaring that, and then taking that power e to the negative value. So the further things get away, the more foggy they should look. We effectively have less level of detail for those objects that are further and further away. We tend to have other approaches now to do level of detail optimization versus just kind of covering them up because we don't want to actually render all the detail associated with them. A little bit of the plumbing and final mechanics associated with our shaders. You saw this, but I don't think enough teams got to enough of this to doing this in MP3. We do have to do an explicit association of our variables and our data. So um, we already are doing this for our vertex attributes, right? That's the input type to our vertex shaders. All of the vertex buffer objects are for that reason. That's why we don't refer to fragment buffer objects per se, because it's that intermediate relationship, right? We specify our input vertex buffers that are then fetched, streamed, or DMA'd, however you want to think of it, into our vertex shaders to do that processing. And now in MP3 you have that. And our fragment buffer objects or our fragment inputs, that's the output of our rasterize, right? So it is a different relationship, even with the unified shading architecture, that how we specify the inputs does differ from one type of shader to the other. For vertex shaders, we're specifying explicitly, here's all the input attributes, here's what each vertex is going to have coming in. Some things are required, other things you then add on top of that. It has its own outputs. For the fragment shaders, it's all based on what the output of the vertex shader is, what is being then rasterized via your rasterization hardware. Separate from that, that's kind of the varying values that are per vertex, then later per fragment. You then have your uniforms. That's your sort of constant data, right? That's your per draw call constant data that is used to configure things changing on a frame by frame or draw call by draw call basis. And we were seeing that issue, right? We would like to cache, presumably, those uniforms, like we want to cache all data memory because our latency to access data memory can be very high. It can be dozens of cycles for our infrastructure we have in class. So it's nice to have that cache. We can get the value back in a cycle or two cycle or a few cycles. But for things that are only constant on a draw call by draw call basis, we have to be careful. We have to actually actively manage that cache and recognize that these things that I have cached actually are no longer going to be consistent with what we have as the backing store in our main memory. And so for teams that are still seeing a shape-shifting triangle that's just sitting there, and it's sitting where it originally was supposed to sit, that is almost certainly the case of what you are seeing, which is you're updating the uniforms, and we'll talk about the mechanics of doing that updating of uniforms. Um, they're getting pushed to memory, but your shader core is not seeing those updated values. So having some mechanism to flush caches, this is becoming more and more important. We've been saying, well, it'd be nice if you could flush the cache in your render output, um, so your triangles don't look so jagged at the very end of their render. It'd be nice if you did it. Some teams kind of did it, other teams kind of sort of didn't do it. It's imperative now, right? Your shaders do not work without flushing those data caches, and they also don't work all that well if you don't flush the instruction cache as well. But you could always find workarounds for that. Now, as we look into MP4, where we're doing a lot of sort of the post fragment operations, where we're doing depth testing, we're doing potential alpha blending, you really need to be able to flush those caches as well for that reason. We need to be able to get that value stored in memory and consistent with what's in memory between draw calls. We'll talk more about that, but I think teams are starting to experience that you have this API call that makes perfect sense. You have GL clear of both color data and depth information. Now we're adding, clearing that depth buffer. Sorry, I'm rambling a little bit here, but what that means in practice makes a lot of sense. Okay, I'm clearing. I'm going to copy, overwrite, tell this whole region of memory, both associated with the color buffer and now associated with the depth buffer. I'm going to set it to whatever that clear value is, and we have an API call that very clearly says, here's the value that you want to clear those memory regions to. What does that mean from your hardware's perspective? It's best to think about that now versus, well, we got something and it didn't work because our cache was in the way. That's absolutely going to happen again. We can't ignore that anymore, I think, for MP4. Probably can't really ignore it for MP3 either. We have to be aware of that trade-off. But in terms of the mechanics of what's happening with our uniform variables here, that's really the big job of that sort of linking operation. It is not so dissimilar from linking any application we're used to kind of natively compiling on our systems to run. It's a little different though, in that really linking refers to connecting that mapping between the various shaders that we have in our system. GL compile shader is our syntax check. Do we meet the spec? And for our purposes, in terms of our driver infrastructure, that's where a lot of the actual assembly translation and all that stuff is happening. Linking programs is where we then determine that for the shaders we've currently specified as active as part of our program, do they correspond to each other? Does the output of the vertex shader match what is the input of our fragment shader? Because if it doesn't, there's no magical understanding by which we can connect via the rasterizer one to the other. That's where we see a lot of our compromise with our infrastructure. We have this fixed size FIFO. We have 16 floating point or fixed point attributes we can kind of flow through our system. So we're pretty limited in terms of what we can support. If you want a 17th attribute right now, you're kind of out of luck. But even so, we have to be very explicit with regards to my output of this vertex shader then corresponds to the input of the fragment shader for my attribute data, and then for my uniform data, that linkage also has to occur. That I have to now be able to query the program running in my shaders to say, where are your uniforms? Think of it like the symbol table if you want to. We tend to have to be a lot more explicit and say, this uniform is at location 0, this next uniform is at location 1. But we have to query that effectively a symbol table to say, where is this uniform? I'd like to update that uniform. And that's the code that was, for the most part, provided for you for MP3 to do this kind of thing. So where are my attributes? Well, we already have been using that, or just updating the attributes by number. So we've been kind of assuming that attributes all have locations specified. But for our uniforms, we'd either be by doing it by name or by location, or by directly querying the name. So in the beginning of our programs, when we want to then update those uniforms, there's something that's basically doing a symbol lookup. So I have a uniform and it has a specific name. If it doesn't exist in my program, this is going to return, I don't recall if it returns -1. It's not exactly an error. It just lets you know that it's not actually found in your program. So in our OpenGL, we are sort of responsible for doing things that we think of a traditional linker as doing for us in our program. I have this variable. I'd like to update that variable at various times in my program's execution. I have to request and get effectively a handle associated with it to say, update this variable. Then the driver would then know, well, this is going to correspond to this location in memory because I've linked this whole program together. Most of that was already in place for you, but then understanding how to interface with that, is an important consideration. So we started to look already at the various different types of uniforms, what you see in terms of the update functions versus what the data has to look like for those update functions. And I think most teams only implemented 2 additional functions for MP3, which is all I wanted you to do. There's, for all the different data types, for all the different sizes of data, there's a different GL uniform function. There's over 30 of them total. They're all very similar. If you had to implement all 30 plus, you could have done it. It's not it's just a lot of extra code, and I don't think it adds much to your learning in the class. But for example, there's GL uniform 4F, right? So the uniform calls take this index. That's the result of that location. So it's a handle, it's an index, it's some way of keeping track of where is this symbol in my code. Ultimately, in the driver space, where is this located in memory? And the calls all would look like that. So update my uniform of this type. It's four floating point values that I'm updating. So it's a vec4 of which I'm explicitly providing four floating point values, and it's going to correspond to that particular index. A little bit in our MP3 debugging, we saw that matrices are a little bit more annoying. That you can specify all sorts of data via that matrix call. In this case, GL uniform matrix 4FV has a number of additional inputs to it. We still specify the index, again, 4F, meaning we're still specifying four floating point values, but we're doing so as vectors, and the idea is we're specifying entire matrices here. So these 4 by 4 array types is what we're specifying. We can directly specify whether the matrix is transposed or not. Um, and there was a lot of double negatives in our thought processes. We were trying to figure out, well, we know that the GLSL model assumes that these matrices are stored in column major order, which is the exact opposite of what our C interface expects for the matrices. So when I want to transfer C matrices to driver space for the GLSL space, we actually do generally want to transpose those matrices first to get the right result from a memory layout perspective. Um, Truth be told, my advice that I gave at the time is the same as what I would give now. You have a 50-50 chance of getting it correct. That's what I meant by that, right? So you either transpose 0 times and it's wrong, or you transpose once and it's wrong. Um, those are your only two choices, right? So uh, try them both, see what the results make sense. If the matrix is giving you the result you would expect it to have, because I think it's easy to kind of do some double, triple, quadruple negatives and get yourself wrapped into a pretzel where there's a different memory model for both. We're generally creating the matrices in C world or in our OpenGL API, and then there's a different layout associated with them in our GLSL language. As long as we're consistent with how we're doing that, you're going to be okay. But don't transpose it in the C space and then set transpose equals true separately, because then you'll get that double negative type of scenario here. And then it actually allows us to specify more than just one matrix at a time. We can actually specify a vector of matrices as well, and that's what that 3 is doing here. Um, there's all sorts of reasons you would want to be able to do that, but for our purposes, I kind of like keeping each uniform with a separate name for each matrix, and then specifying just one single matrix at a time. Technically, this would be fewer update functions, fewer copy operations, and it would be more efficient to do 3 matrices at a time versus 3 separate matrix calls with just the value 1 there for our count value for our matrix call. But that's a pretty, for me, that's a pretty clear trade-off between clarity of code and performance of the code. And I always try to go for clarity, at least for this class. And once your uniforms get large enough, then you can start to look at, well, if I have enough uniforms that I actually need for my draw call, maybe it makes sense making that another vertex buffer object instead. If here it's 48 floats, that's not so large. If for some reason your shader needed hundreds and hundreds of these matrices, having them as uniforms may not make as much sense. Having them as a buffer object would be maybe a more natural way to interface with that data that you have there. So here's our cube flyby application, and I just wanted to show what this thing does in practice. Right, most teams did not get there yet, and part of the issue with cube flyby was definitely that without depth information, it looks very flat in hardware. But that is changing, right? So those who've been concerned that this feels like this is a 2D graphics class, it's not. Well, first off, it's not. It is very much. We're covering 3D techniques throughout. We have almost everything in place to show 3D things rendering on the board. It just tends to be a lot easier to talk about things in 2D first, to test things in 2D first. And then as you add that Z dimension now and you have it and you're actually using that information in MP4, things should just sort of work. You may have to go back and look at, well, when I rasterized, did I kind of just ignore the depth parameter? I don't think most any teams did, but that's a fixable mistake if you did that. But we are doing 3D stuff. It's just when you're testing, and certainly when you're testing, with ILA and you're trying to grab and test individual instructions running on your shader, keeping things as simple as possible is still very much the way to go. So this program, and I did tend to think of these programs as master program 1 or get it really good and then worry about program 2 and then worry about program 3. But I understand, if I give you 3 programs, you want to test all 3 programs. The actual geometry of this program is relatively straightforward, and all it's doing is showing a three-dimensional cube and showing how when we update the matrix associated with our model view projection, and as we look at the shader, it's called that MVP transform. That's what the MVP stands for, not most valuable player or whatever, but model view projection matrix. Sometimes we keep those as 3 separate matrices: a modeling matrix, a viewing matrix, and a projection matrix. Sometimes we separate them for reasons into 2. So you'll see a model view matrix and a separate projection matrix, which we multiply together. And oftentimes, depending on what we want to do, we'll have just a single modeling, viewing, and projection matrix that we do the initial matrix multiplication in OpenGL space. Oftentimes the library, if we're using GLM, is doing it for us. We don't really even see it. But we do that initial matrix multiplication once, and then we pass that entire combined MVP to represent for a given object what we would like that view to look like. That's both scaling the object and, if you think of viewing, placing the camera and setting the camera. And then for projection, describing what type of camera it is. Is it doing a perspective view? Is it doing an orthographic view? We combine all of those into a single matrix. That's why you'll see this term MVP. That's what it's referring to. It's the M matrix, the V matrix, and the P matrix sort of pre-multiplied together and copied over. And that's what's happening with this application. So this application, you just kind of mess with the keyboard, and it just, in somewhat arbitrary ways, I believe it just updates the camera position. So again, we talk about the equivalence between modeling and viewing, right? Am I moving the object or am I moving the camera? Well, the answer is always kind of both, right? Because they're equivalent to each other. I'm rotating, or I think in this application, we'll look at the source here in a moment. I'm placing the camera at some location in a three-dimensional space. That is equivalent to moving the object, right? They're equivalent to each other. Is the camera moving further from the object, or is the object moving further from the camera? The matrix and the resulting math is equivalent. But in this case, I think I'm using the functions that specify the camera locations to update that matrix. So in terms of what's happening here, certainly yes. If I asked you to implement this function with MP2 hardware, you could do it, right? How you would do it is you would have a lot of code running on OpenGL to take my initial set of vertices associated with my cube. You just think of a single triangle if you don't want to worry about the cube, right? The cube looks kind of ugly here anyway, but I would take the vertices associated with that triangle, and if I only had rasterizer hardware with no programmable shaders associated with it, you would do all that computation in, I don't want to use the word software, but I'll say in OpenGL space, right? You would pre-compute what all the new vertices would have to be as inputs to my hardware every time I want to change where the camera is. It's valid. I mean, it's mathematically the same, right? From a performance perspective, think about what's happening here and what makes programmable shading so powerful here. You could do that, and this is, I guess, for a cube, is it 28 or something like that vertices? It's not that many vertices, but this is just one very simple cube that isn't doing all that much, right? You could pre-compute in OpenGL what all the new vertices could be for every time I press my keyboard arrows here and change where my camera is located relative to the object I want in my scene. And that would be valid. And each time then you would have a draw call for every frame. You would then, every time you would change the camera location, you would want to update your vertex array object and your buffer data and resend that over, recopy that over. Well, if it's 6 sides, so if it's 12 triangles, who cares, right? That's not so bad. So 36 vertices. I was able to finally do the math, right? 36 vertices for this application here. That's not so bad. But for real scenes, when you're looking at thousands, hundreds of thousands to millions potentially of vertices, that becomes quite bad. Whereas now for this application, what are we really doing? We're sending the vertices over once. They are fixed. In fact, if we look at our code for this, let's see if I can open this up here. Yeah, I got it here. Um, the actual triangle data is static. Those are our positions, and those are I don't recall where I got the values for the colors associated with that cube. They are sent once, and you can look at the code. You don't have to believe me on that, but the actual for us, we copy it when we get the attribute pointer code, but conceptually, I could also see the copy happening in the real world driver space when you get that buffer data. That call only happens once. 36 vertices, that's 36 XYZ, 36 RGBs, send them over once. Also, as we're doing that, and I think the code is maybe even before the vertices. It doesn't really matter where it's located. Here it is. We use that load shader helper function, which is doing all those same steps we talked about. Create program, compile, load shader, compile. All those function calls happen basically one after the other for our vertex and then for our fragment shaders. And then we have this extra code here, which is that's our get uniform location. So literally, look inside the blob now associated with our shader, and let me know what index is going to correspond to a uniform called MVP. It has to be called MVP. If I change that to MVP2, or if I change the actual shader to call this MVP2, this OpenGL code doesn't work anymore. Which is why, OpenGL code that tends not to use static shaders stored in a text file somewhere tends to get pretty messy, right? Because you're doing a lot of potential dynamic generation of shaders, potentially either based on compute capability of the hardware it's running on or just based on changing needs of a particular scene. And then your OpenGL code also has to be aware that that's happening. In our case, we save it as a text file. We try not to change it all that much, and then our OpenGL code is also pretty static. But in reality, you tend to see quote unquote real world OpenGL applications. Take a look at the example I provided. I think GL Quake is too much of a lift for us, but GL Doom may be actually doable, even though it's a more advanced game. The engine it's written with is something that I think we can work with. It doesn't look a lot like our CPRE 480 code because you won't see, for the most part, these .vert files in there. There's a lot of querying of, well, what actual hardware is this running on? You'll have code, well, if this is running on a 3DFX Voodoo 3, we're talking 1998 hardware here, make your shader do this, otherwise have your shader do this, and then dynamic shader generation based on the needs of a particular scene to load or not load as needed. The corresponding OpenGL code, it's calling all the same functions. There's no change associated with it. It just tends to not have a lot of constants in the code as well, because this kind of co-design of OpenGL and shader code is kind of awful from a programming perspective, right? You get these weird silent errors because someone's made a change to a shader and you have to update your code accordingly. But all that being said, logically, it's still the same exact functions that are being called, which is give me an ID associated with, think of it as a symbol table, think of it as just an index into a blob, where in memory that uniform is in my code. And so when we move the camera in this application, we actually, well, there's some key press functions. So we're changing some global variables based on key presses that are happening here. We have a code here. We'll talk about the first part in a second. That actually uses that ID, also as a global, uses that ID as our index into our GL uniform matrix for FV call. In this case, given that index, that we needed that call to return something greater or equal to 0, a valid index, we're going to send one matrix. We're not going to transpose it. I'm not entirely sure what would happen if we did transpose it, change it to true, and we're giving it a pointer. And GLM gives you a couple different ways to specify that pointer. So you may see GLM code that just specifies the term MVP here because I believe the library is smart enough to also return a pointer when you. There's other ways to return the pointer. You can do it in the old school C way of give me the address of the actual first element in that matrix, and that also works. But GLM gives you a couple different hooks to do that. Otherwise, what's happening here is well, we're using a couple of those functions. So we're using a function first for our viewing matrix that specifies my camera location. And there's three things we need to know. I know we covered this briefly, but there's three things we need to know as we specify our camera location. Where is the camera located? We call that camera location. It's the eye. And so it's where are we viewing from? What are we looking at? And this is one such function we can use for it. I think it's a pretty intuitive one, so I like it. Where are we located in three-dimensional space? What are we looking at? In this case, we're just looking at the origin. That's how we set up this application. And which way is up? Because you do need that as well. Because what is the orientation of the camera? If I were to change the up vector, it would appear to be a rotation of our cube. It's logically still equally valid, but in this case, we're saying positive y direction is up. At least when you're thinking about objects and you're getting started, that's a natural way of thinking about up. But it's all relative to what type of rotation you potentially want of your object. That's our we can call it our model view matrix there that we specified. We also could have specified that using the type of functions that say scale f or translate f or rotate f. In this case, this is a nice way to say here's my camera. Here's what it's looking at. If I want my object to be smaller and further away, I specify my location as being further away. If I want to get a top-down view, I rotate my camera around to the top of the object and point it downwards. And then we also here are specifying our projection matrix. We didn't talk that much about the functions for generating the projection matrix. I was worried we were all getting a little bit bored with that, but maybe you were just really excited to learn more about that. But that's setting the field of view. That's that first input there. And that's setting basically the clipping space for that particular object. So what am I looking at? What does my frustum look like? And that's effectively what you're setting with that function. We can also, and that's a type of function that gives us a perspective view, right? That's generally for looking at reality. That's a more realistic way to view things, where things that are further away should appear smaller to us. That is in comparison to our orthographic camera setup, where everything is kind of flat and we're just doing a parallel projection on the thing. So in this case, though, it's a little bit of an in-between of we could have specified both matrices as being uniforms in the code. It would have been equally valid. And we could have had our shader do the multiplication for us of the projection matrix times the viewing matrix to get our MVP matrix. The order of these matrices does matter. In this case, I had no need for this model of a cube to look at the viewing matrix separately from the projection matrix. So we just do the multiplication once in OpenGL space, and then we transfer that entire matrix back over. Now when we look at our vertex shader for our cube, it's not doing all that much. Our input is our position. Here I was just trying to be a bit more explicit. When I talk about vertex position, that is literally the position given in our input attributes, which is given in model space, right? That's our cube. Our cube doesn't know where it is. We define our cube our models relative to the origin usually, because we're going to move them later and translate and rotate and scale them later. We also specify the color as just that second attribute associated with each vertex as it comes in. We're going to also then just generate a color here. It's not misleading, but we're just required to generate a position value that's a built-in of this vertex shading model. So you can think of there as being two out vec4s. One of them is just a built-in, a requirement of the vertex shader, so we don't have to specify it as such. Then we specify our matrix, our 4x4 matrix, which is our MVP matrix here. And after all that, we're specifying our position just with a vec3. We could have also specified it with it as a vec4. Instead, we just concatenate the W component of 1.0. We then do the matrix vector multiplication as it comes in. And then finally, we're setting the color just based on we don't have alpha blending, so the alpha is kind of irrelevant what's happening here. But we just specify kind of a pass-through for our color information that comes in. So what you should be seeing in your MP3 hardware is a very flat looking um, rectangle for this. Because we're not in hardware doing any processing of the depth information, the order in which we actually render the triangles matters quite a bit. Because they're just going to be, we talked about that kind of painter's algorithm where, right, you're drawing the little clouds in the background and then the mountains and then the trees in the foreground and things like that. That's what our hardware is doing for us, whether we want it to or not, right? Our render output, the module that you currently have, not with any MP4 stuff in place yet, but what we've had since early in the semester is fragment comes in, I push fragment to memory. So in this case, we're doing our rendering on a triangle by triangle basis. Your MP3 code should be doing all the correct manipulations of those triangles. It should be able to do that matrix vector math for you quite correctly, but the order in which we specified triangles will dictate as we do the manipulation of them and they all get pushed to our render output post rasterization here, which ones you're actually going to see on your monitor attached to your FPGA board. But the only difference, there's two, one more important than the other. But the only major difference between what we're seeing on the screen here and what you should be seeing on your board is until we get to this week's lab. And I think it's really doable. So I'm looking forward to seeing people getting some 3D looking things working for MP4. It's logical, it's straightforward. There's a few API calls and there's some cache issues and things like we've been dealing with. But it's very doable. But that's the major difference. Where in this case, in our actual hardware, we have a default depth function. We don't actually have it in the code, but there's default assumptions. There's a default depth function. We don't see the call in our code, but it's using whatever the defaults are. It's GL less or whatever it's called by default. We are rejecting fragments that are further away in the Z dimension from our camera. Because that's how objects work, right? If it's behind some other fragment that we want to see, we shouldn't have it on our screen. Once you have that in place, you should have a result that looks kind of pretty much like this. The final piece of that puzzle that is going to cause it to look not quite as good is we are doing for our code here, and maybe I shouldn't have, we're not doing this parallel projection, right? We're doing this perspective view. And if you go back to that previous lecture where I talked about what happens in our matrix vector math for our perspective view, well, it's a matrix times a vector. We wind up post multiplication with a W value, a W component of our resulting transform vertices that's not equal to 1 anymore. That's just a nature of the type of scaling and translation that we want to have when we're doing a perspective view of the system. I think it's okay to say that's the way the math works. But if you look at the build up in that previous lecture module of what a perspective view corresponds to in terms of the matrix that gets calculated for it, we wind up generally with using a mixing of the Z with the other parameters here. We wind up with a W value that's not equal to 1 anymore. So what is happening, and completely valid question, what is happening either in fixed function hardware or via some programmable addendum to all of our vertex shaders is we're doing a perspective division. And I just didn't want to deal with it this semester. So our hardware is not doing that perspective division where we take the value of W and we divide every other attribute by that value of W. If W is 1.0, no harm. We haven't changed any of the other values. When we get this, we want to see this perspective foreshortening. We want to take that W value and make things appear smaller, further away, based on that W not being equal to 0. That actually gets applied to everything. That gets applied to our normals. That gets applied to our texture coordinates. That, at least in theory, unless you tell the rasterizer otherwise, that gets calculated for every attribute we specify for our incoming vertices. And so because of that, even though I think it'll still look pretty good, because this is not a lot of perspective, and you can change the keyboard and the camera location so that if the camera is at the same plane, I don't know if it's going to give me a rounding error here, but if the camera is at the same plane with the cube here, there'll be very little perspective whatsoever. This is I don't know if I can get it exactly right. This is basically an orthographic view, right? For the most part, it's not quite this triangle. I've lost my mouse here, but that triangle's a little bit smaller and further away, than the other one, but it's not so much. Um, but what you'll see is something that's not doing that perspective transfer, that final part of the perspective transformation, and so it'll look a little bit distorted, but it'll still look like a cube. You'll know that it's a cube just with a hardware bug. A couple teams have asked about, well, if we know that we need to do this post perspective transformation division, you can call it the perspective division, whatever you want to call it, this W division. Why don't we just do it in our shader? Um, and well, if you have division working, that'd be part of the thing you'd want to look out for in software. And I think the answer is, and I'm willing to admit if I am at some point wrong about this. I mean that wouldn't shock me terribly. Um, I think we can, and it's not that clear to me why we can't. So you would get something like GL position. eh, You may want to declare a separate variable, for that versus updating the GL position. I don't know if it'll even let you do that. Something like that, because you can do division of the vector by a scalar in your syntax. Something like that should be okay. The main question that I'm not really sure of the answer to is in modern hardware, this issue of to what extent do we still have dedicated fixed function hardware for anything is still to me a very open question, and I would include that in it as part of the open question because to me, I could certainly see our compiler you could update our compiler accordingly to do that computation, even if you don't specify it in the shader itself. We know mathematically in terms of the rendering pipeline that division is happening. I don't know if we're going to get a syntax here. I mean, maybe we can try. I mean, I'm not afraid of getting a syntax error, in the middle of class here. I mean, it should give us the same results, and it does, right? It doesn't break anything, no matter because either that division happens in our shader or it's happening in our maybe fixed function hardware. But again, what to me I'm leaving as an open question is we already have these shader cores that can do division and do division relatively efficiently, maybe more efficiently than our division that we're having to kind of compromise given our lack of space on chip for it. Why not do this? Right? I'm not specifying it, and it's definitely not a requirement that we specify this, as part of the shader itself. That's definitely never a requirement you do that yourself in the shader. But we have a compiler, right? A shader compiler that generates assembly code, and whether the assembly level it gets inserted or whether at some just in time compilation happens when it gets loaded into hardware, why not just do that? Recognition that we have to do that perspective transformation, just do it in software. I guess that's my thought. I don't know the answer to that. So from our perspective, you have a couple different choices. Then you could consider something very comparable, which is, and we're already doing a little bit of that, which is kind of a post processing of the assembly input and output that we get to add some fixed functionality. We're doing pre-processing to do our in FIFOs and post-processing to do our out FIFOs. If you look at the compiler, the Lua code, Steve's baby to generate that, we're already doing some post processing. I don't see why we can't also do that as post processing as well. But when you get to that point of you have a cube working on your monitor, so working in hardware, and you'd really like to get rid of that warped kind of fisheye sort of view of what's happening in it, that would work. It's just new. It's not necessary in real hardware. So why is it not necessary for ours? Well, we either have to add a fixed function piece of hardware that always does that division for us, or in our compiler infrastructure or driver infrastructure, we have to add that as kind of an addendum to what our shader compiler otherwise is emitting. I don't know if that made any sense. So let me take a moment if there's any questions about what I was just talking about with that. So big picture point I was getting at was just shader mechanics. So how we're passing in this MVP and why we want to do that. We don't technically need to. For MP2, you could have done it yourself. Do it all entirely in software. Transform not just a single matrix, but transform every vertex position in OpenGL space. It's going to be a lot more performant to do so in hardware. We already have the hardware here. We have a lot of vertex shaders. There's a lot of, well, in theory we do. There's a lot of inherent parallelism, at least in theory. We send the vertex data once. We do that expensive copy once. Then at compute time, we can keep those pipeline pretty effectively. That's why we have this capability here. This final question of specifically this application or any OpenGL application that involves perspective viewing of the system, where does that final step happen is unclear to me. I'm not afraid to admit that. For our purposes, I didn't want us to worry about adding any more fixed function hardware at this point in the semester. We have enough going on. For our purposes, if you don't like how this cube looks, even after you have depth stuff working for MP4, and if you have division working, that would be the next thing to worry about. But if you have that working, that this operation should give you the equivalent result in hardware with what your OpenGL is providing for you. Because OpenGL is doing that operation inherently in the rendering model, in the graphics pipeline model. Where is it doing it? I don't know, but it's getting done. We can be explicit and just have the shader do it for us. Okay. That's shaders in a nutshell. I really want to talk about lighting. I mean, a couple different shaders that I also wanted to show just as examples of just playing around with vertex shaders. Like everything OpenGL, you do have to be careful when you look up examples online, as I did here, of what version of OpenGL they're supporting. How old is the code? Old code's not necessarily bad, but oftentimes you have to be very explicit with what version of the shader language you are supporting for certain very specific either features or requirements of the shader. But I kind of like this example because of just what it looks like. So this is the Utah teapot. We call it Funky Teapot here, and it's the same model. Um, and well, what's happening in this model? Can we figure out, right? Well, first off, it doesn't look very three dimensional. So the teapot did look three dimensional to us before. To get things to really look three dimensional, you either need to have some lighting model or something. But it looks very two dimensional to us, to me at least here. If we look at the shader for this example, it's getting really flattened. So this is using an older shader model, but it's fine. We're providing as an input a single float just called time. So you can imagine what the OpenGL is doing. It's running a clock, right? Every time we get a new frame or we're done with the frame, we increment some floating point value called clock, and we send it to the shader. And then it's just doing something kind of silly with that clock, right? So taking the x position, multiplying it by 5, adding time, and then calculating a new z value associated with it. And that's what the result is we get there. So let's take a minute and start with this shader and start with time. I mean, we could do things that require starting from scratch. We just won't really get to it. What else can we do? I'm open to suggestions. Let's take a couple minutes. Assuming you just have a single uniform and we're assuming a Utah teapot coming in. This is also the old school way of specifying the model view projection matrix, but it's fine. Assuming we do have a view of the system, we have input vertices coming in, and then we have a time varying parameter here. What other fun things can we do? So that I'd like you to take a minute and come up with an idea. As I'm excited. So make it trippy like the '90s. Unfortunately, with this stupid shader, we can. In this case, it's also using kind of a fixed fragment color, and I don't have the plumbing for connecting those, so we could try it. This is the older syntax, so it'd be something like varying float color. Let's see if that works. If I break this, I will unbreak it. And then in our fragment shader, we'd have something like the same declaration. So that would allow us to, if this works, that would allow us to mess with the color in the vertex shader versus the fragment shader. We could do some pseudo random code generation. Let's see if this works or if I killed it. Since I'm just changing the shader, I shouldn't have to actually recompile anything. What did I do? Implicit narrowing from vec4 to float. Yeah, what am I doing? You guys should have caught that. Come on. color has to be, four values here, right? Not just a single value. I don't recall. I think if it's a Vec 4, we'll see. This is an older shader model it's using by default. Okay, we've got our funky teapot back. Um, I think if you specify things as Vec 4s or Mat 4s, that was in the slide, but it really does depend on the version that you're talking about. I think by default it's all floats if you specify those composite types. So okay, so now we have a funkier teapot. What can we do with it? So now you do have access to color. Um, because I now the fragment shader is literally doing nothing, which is fine. It's just a pass-through fragment shader, and now we have color access to color. So I'm open to suggestions. So your suggestions are fine, but let's do code suggestions versus just idea suggestions. Um, what can we do? Right. So I guess another thing to say is if we want to go back to um, our like what was it supposed to look like, I guess, right, before any processing. If we want to go to our red looking teapot, we would have the shader look like that, right? That would be, well, it's a top down view, which is fine, but and it's not really 3D looking because there's no lighting model here, but still, that's what we get by default. So by default, if we just do model view projection transformation, and if we just set a constant color, that's what we get back out. What else can we do? I need some code though. I can't just do it just based on high level concepts. So take a moment. Don't just shout out at once. I'll take a look at that link while everyone else takes a minute to play around with this and think about what we can do. So now we have two inputs: the attribute himself, the XYZ location, and a time, which we can assume. I think time is monotonically increasing as an input to this code. Um, we have to do probably the MVP transformation to get anything to be viewable in our scene. But other than that, we can mess around with color. We can mess around with that intermediate vector V. In fact, I guess another way to say that would instead be not comment out that line, but instead to just comment out that line. That also should have given us the same exact result. So take a moment and think about what we can do with that. Yeah, there we go. That can be one of those links, Matt, that breaks my web browser, though. Appears to be so. I can't even load it. So that's a good thing. No, can't get it to work. So that's a no. But take a moment. This will be the last thing we do today. That's fine. Let me leave the code up so you can see that while instead of the screen. We can give that a try, Matt. Let's see what it does. Thanks for trying something. I guess I should have mentioned. Yeah, I have a. I didn't actually create the link, so that link there would also be helpful for page 7. I apologize for that, but you could go back to the slides, or you could look at page 7 and 8 of that link down there. Just the quick reference card for the GLSL shorthand for the kind of things you want to work. I didn't provide that. By and large, my experience has been if you can think of a mathematical operation that makes sense, it tends to be supported. So you don't have to have the reference handy by and large, but just for inspiration, that could have been useful. So color equals cosine times sine 0.5 times some. I don't know. We can give it a go. Let's see what it does. Well, Jared, you ruined my fun earlier in the class, so I had to kind of um, so I had to add a little bit more for today. Um, let's see. So cosignage, I feel like it should wrap around though, right? As you keep incrementing time. Oh, there we go. Just a little slower than. I mean, we can change all the constants associated. So there you go. You have your color changing kind of shader associated with it. So it's kind of cool. So actually, I think this is actually a pretty good stopping point for us. Um, so thanks, Matt. I appreciate the suggestion. It did. Changing color as a function of time worked fine, and probably any combination of time and color would have done something. Um, you could have done different constants or different trigonometric functions for each of the different color channels, and then you would see a pretty almost non-deterministic looking color we would have associated with it over time as those things uh, don't necessarily have the shared frequencies. But that looks pretty cool too. I think this is a good stopping point. But the reason I say that is what I really want to talk about is a topic that doesn't necessarily have direct hardware implications, but is really just an extension of this, which is what does it mean to do shading? So shading is to pick a color of our fragments ultimately. How do we do shading so that it doesn't look, you know, flat like this? And that turns out to be fundamental inspiration for all sorts of different things we do in OpenGL and all the reasons we have all these features in GLSL. How do we support lighting properly to make this teapot look like a much more three-dimensional teapot um, than this very flat-looking thing that we have here? So it's not just an issue of doing the geometric transformations. We are still doing that in this code here. We have a camera. It's all specified in a three-dimensional space. But despite all that, and we're doing Z buffer and all those sort of things, despite all that, what we see is still a very much two-dimensional looking teapot. And I'll show it here again because it's just all a single shade. It's all a single color. So what we're going to talk about starting next Tuesday is, what kind of models can we apply? What other things can we do in the shader that using the same class of functions, a couple uniforms, a couple matrices, and just our input vertex attributes. And how do we get back out something that actually looks three-dimensional? We were able to do it previously via just having a wireframe view of something, but that's generally not what we want. For a solid filled object, how do we get them to look realistic, and what does that mean from our shader's perspective? I appreciate everyone coming to class today, and please do click on that last link I left. That's a pretty cool demo for the shader toy technology. It's worth your time, certainly after class is over. Otherwise, I look forward to seeing everyone's progress next week, and I'll see everyone in class on Tuesday.